Dear everyone, my name is Fan Chen, a final year PhD student from National University of Singapore. My supervisor is Professor Wentao Yan. The topic I'm going to share today is the data-driven prognostic model for temperature field in additive manufacturing based on the high-fidelity thermal fluid flow simulation. Our group mainly focuses on the multi-scale multi-physics modeling of the powder bed fusion process. And the grain growth model and the thermal stress model are all mainly based on the accurate temperature profiles extracted from the thermal fluid flow simulation. And for the thermal fluid flow simulation, the computational cost for each case is quite high due to the incorporation of lots of physical phenomena. And the pre-processing of the temperature profiles is quite sophisticated, and the temperature loading process from the temperature profiles into the grain growth or the thermal stress model is also computationally expensive. What we are trying to do is to build up an algorithm uh, which can predict the temperature profiles without directly incorporate the heat transfer of fluid dynamics equations. And the overall framework is like this. Firstly, we conduct a series of thermal fluid flow simulation cases, and for all the cases, the multiple temperature field can be characterized by a series of function parameters of the isotherms. In this way, the input-output pairs can be built up, and all this data can be implemented into constructing the regression of machine learning algorithms. And for unknown input manufacturing parameters, it can be input into the model and predict the temperature field. And for the temperature field, we will not directly evaluate its performance. Instead, we will implement them into the thermal stress model or the grain growth model. And the simulation results will be compared with that using the thermal fluid flow simulation temperature profiles. For the temperature field parameterization, here I show a simple example to show how we extract all the isotherms from the thermal fluid flow simulation. And for the temperature field, we only visualize the half due to the symmetry. So for the temperature field, it can be represented by a series of isothermal surfaces, and each surface consists of many isothermal points. And in reality, we can hardly extract the data points whose temperature value is exactly equal to T. However, we can set up a tolerance here to extract all the data points whose temperature value is within this range. And each isothermal surface can be cut into many pieces along the vertical direction, and along the horizontal plane of each piece, the isothermal points can be fitted by the isotherms, and the isotherms is characterized by the function parameters, and therefore we now have three output variables, that is the two half lengths and the y's. All the isotherms are extracted within the temperature range of 1000 Kelvin to the liquidus temperature of the material. And the region whose temperature is above this range, it will be the liquidus phase. Liquidus phase will hardly affect the residual stress and the grain growth. And for the region whose temperature is below this region, the phase transformation and the grain growth barely occur, and the residual stress that also not change too much. And the accuracy of this data extraction is determined by the contour numbers and the mesh size of the CFD simulation. As we can see from the figure, if we choose too many numbers of the isotherms, the half-wise B will be inaccurately captured. And these contour numbers should neither be too large nor too small. And the smaller mesh size of the CFD simulation may increase the accuracy of this data extraction. but it at the same time will increase the computational cost. Due to the difference of the curvature and the temperature gradient, the whole region of a isotherm will be split into two subregions, and the split line is chosen between the two endpoints of the maximum Y segment. Along this segment, all the CFD data points have the maximum distance to the symmetric center line. And in different region, the curve type is different, and the temperature tolerance for the data extraction are also different. And the split line cross the symmetric center line at the reference point. This reference point is critical as it determines the relative position of all the isotherms. Within the symmetric central plane, we are trying to find the rules of the distribution of different reference points. And here we choose three different positions to observe the distribution, and two endpoints and the center points of the maximum Y segment, as I have mentioned before. And we observed the Dell distribution in many other samples and found that the central points are always well aligned, while the two endpoints are highly irregularly distributed. And in this way, we can fit the central points with the straight line, and this straight line can provide the reference for the relative position of different isotherms. And once the relative distance of the top points are determined and the slope angle is determined, the position of all these isotherms can be determined and they can be combined together. And here we have three more output variables for the prediction. One is the relative distance between the top points of the reference lines to the base point, and the slope angle of the reference lines, and the layer numbers of the isothermal surface, which represent the depth of the isothermal surface. The input of the algorithm are the manufacturing parameters for the thermal fluid flow simulation samples. Those are the power and velocity of the heat source of samples numbered from 1 to 42. Each case takes about 100 CPU hours, and for each case, we extracted the geometry features of the isotherms that is represented by the output variables we have just mentioned. And, then we use the data-driven algorithms to find the mapping relationship between the input and output variables. For the data-driven algorithms, we tried many different regression methods and the neural networks. And two main factors we will consider in choosing different algorithm is the accuracy and efficiency of the algorithm. And from the testing, we found that the Gaussian process regression and the quadratic regression can achieve very good accuracy in predicting different variables with high efficiency. For the curve fitting of the isothermal points, we choose different fitting function in different regions. And besides the ellipse function that has been applied by many researchers into fitting the isothermal points of the multiple temperature field, we also tried the polynomial function with this style. And once we know the dimensions of the isothermal points set, we can determine the two parameters C1 and C2. By changing the index, we can calculate the fitting performance of different polynomial function. And we tested the mean square errors among 26 samples and calculate the average mean square errors. The ellipse function achieves quite remarkable fitting performance, while if the index is properly chosen, the fitting performance of the polynomial function may achieve even better performance than the ellipse function. It is more straightforward to see the performance through the figures. you can see that the index 1 achieves very good performance when the value is 6, and in the region 2 the optimal choice for index 2 could be 3. And for different cases, this index setting for the fitting could be slightly different, but the uh, the range of the choice could be similar. Therefore, for index 1, we will choose from 5 to 7, and for index 2, we will choose from 2 to 4. And furthermore, we tested the predicting accuracy of different algorithms in predicting different output variables. And we found that for the layer numbers and the slope angle, the Gaussian process regression achieves the lowest mean square errors. Therefore, in the model, we will use the Gaussian process regression to predict the layer numbers and the slope angle. And for the length variables like the relative distance and the isotherm dimension, we will use the quadratic regression to do the prediction due to the lowest mean square errors. We also predicted the isotherms on the different training data sets, and we found that the prediction on the 40 training samples is very close to the ground truth already. Definitely, if we increase the training data set size, the prediction would be more accurate. But as I have mentioned before, the computational cost for each sample is very high. Therefore, we only use 40 samples in the following prediction. And once we get all the predicted isoforms, we will do the temperature field reconstruction. And for the temperature field within the molten pool, we will use the peak temperature to do the interpolation with the liquidus temperature of the molten pool boundary. And in the outside region, we will find a influent position whose temperature is assumed to be the preheating temperature to do the interpolation with the 1000 Kelvin of the boundary. And for the inside region, any point is surrounded by a set of the isotherms which are located on the two horizontal planes. And the temperature calculation is based on the global baseline. And we can always find a plane where the point G and the global baseline are located within this plane. And this plane called the two horizontal planes at two lines. And in this way, we can use the 2D linear interpolation to calculate the temperature values of node G, as we know the coordinates of the points surrounding point G based on the fitting curve functions. And also the temperature values of these 4 points are known. It should be mentioned that that in reality the situation could be more complex than this one, but the basic idea is similar. And in this way, we can apply the predicted isotherms into the FEM model to simulate the thermal stress. And here is the comparison between the predicted result and the original CFD result of the testing sample. And we can see that in the region 2, the temperature difference is quite small, and the larger temperature difference exists in the region 1 because the predicted half length in region 1 is slightly larger than the CFD results. That means the molten pool size in the CFD results could be slightly smaller. And if we compare the similar region ahead of the molten pool, the temperature level and the distribution would be similar. And we choose 3 points to observe the thermal history, and different index and different set of contours are selected to predict the temperature field and implement it into the FEM model. Node O and node Q are at the molten pool boundary, and node P is inside the molten pool. And from the thermal history, you can see that on node O, and due to the under prediction of the multiple Ys, the temperature magnitude is slightly smaller than the ground truth, while in the node Q, due to the over prediction of the multiple depths, the temperature level is slightly larger than the ground truth. But overall, the uh, the deviation of the temperature history can be very small if we choose the suitable index setting and the contour numbers. And furthermore, we chose node P to record the thermal stress history. And from the result of the missile stress prediction, we can see that the index setting of 5.4 with turn contours can achieve very good performance. And for the X stress component, it shows the similar trend and level. The deviation for some of the better predictions, the deviation is within 30 megapascal. And normally in the plasticity theory, the missile stress would be the critical criteria for the plastic deformation. And the good agreement um, demonstrates the potential of our model into simulating the thermal stress history. And in other two directions, the Y stress component, this stress component, the a large oscillation occurs, but this does not affect the missile stress too much because the level of these two components are very small. And then we further evaluated our model by testing the temperature field of another sample using the grain growth simulation. And from the predicted grain growth process, we can see that the orientation of the grains agrees very well with the ground truth, and the average size deviation is about 20%. And there is less grains with high aspect ratio in the prediction because the predicted molten pool depth is slightly smaller than the ground truth. And finally, we compared the computational cost of the thermal stress simulation that used two different kinds of temperature profiles as the thermal loading. And we found that the data-driven predicted model reduced the computation cost by at least 70%. And putting aside the thermal fluid simulation itself, the data preparation process for this model will make this process even longer. And also we applied our data-driven model to do the upscale modeling to simulate the five-track three-layer M case. And in this model, there is no heat transfer process, no thermal fluid flow calculation, and no CFD temperature profiles loading. It's purely based on the data-driven predicted model. And this is just a preliminary result, but from this result, we can see that the this simulation case with over 1,400 steps can be finished within 36 CPU hours. And this computational cost is nearly impossible for any other thermomechanical simulation to simulate the same thing. And these research works have been submitted to the journal and is still under review. And for more details of our research works, you can refer to our group website. Many thanks for listening.